Let's talk about a few items in hypotheses that are involved when we actually analyze the data. The first thing is called the significance level. The significance level actually is just a formal name for the probability of type 1 error. Okay. As I mentioned, since we want to reduce the probability of type 1 error, we usually choose the significance level to be 10%, 5%, or 10%, depending on the scenario. So if this is something critical, if this is something related to a person's life, we will choose 1%. The default level is 5%. That is, most of the time when people choose significance level, or when people choose the probability of committing a type 1 error, we choose 5%. If this is something that is not so critical, then we pick 10%. Like if we're doing something like a survey on customer opinion, or people's preference, if this is not something very critical, we pick 10%. Now, the significance level, how we determine which level? Most of the time, it really reflects the amount of error we can tolerate. Okay, if as a researcher, we get to determine which level we pick, but it's really basically when we conduct the analysis, it's the amount of error we can tolerate. So the p-value is the criteria that we can learn in this course to perform a Formally, p-value tells us the probability of observing your sample statistics if the null hypothesis is true. What does it mean? Basically, when we test a hypothesis using sample data, at the very beginning, we're gonna assume the null hypothesis is true. It's almost like before a trial begins, we're gonna assume the suspect is innocent. Then we look at the sample data or look at the evidences collected during investigation to determine whether the null hypothesis can still hold true or not. So after looking at the evidence, if we decide no, the null hypothesis is not true anymore, then we conclude that the alternative is supported by the sample data or by the evidence. So that's the basic idea. Now, the p-value will tell us how likely can we observe with what we do see in the sample data if we assume the null is true. All right. So let me illustrate this concept a little bit more, because at the beginning, p-value is very difficult to understand. So let me kind of start with this simple example I created myself. Suppose right now we have a box, and inside the box there are 100 balls with a number printed on each one of them. This is almost like the lottery Powerball drawing. So you have the balls with numbers printed on it, and you don't get to draw all of them. You draw a sample of it, right? So what you are allowed is to take a sample of 40 balls. That means among the 100 numbers printed, you are able to access 40 numbers of them. All right. And what I want you to do is to make judgment based on your sample. So this is actually kind of similar to the example we talked about at the beginning of this chapter, when we talk about the employee satisfaction survey there. It could be that there are 100 employees in the Richmond plant, and when you hand out the survey, only 40 of them completed the survey. That's where you only have a sample of your employee satisfaction, and you don't get access to the whole population satisfaction score, right? So now you have to use your sample data to make inference about the whole population. You have to make a judgment as to whether employees are more satisfied based on the 40 employees' opinion who completed the survey, right? And now when you make judgment about employee satisfaction, you actually don't want to make the judgment about the 40 employees only. You want to make the judgment about all employees in that plant, all right? So that's the scenario we have here. Now suppose, all right, you got the 40 numbers, you calculate the mean, and the mean turns to be 21. All right, now I want you to think about the statement I have here. You have a sample mean of 21, and I want you to use that fact to make judgment about the statement here. The mean of the 100 numbers is 75. So my question is, how likely for this statement to be true if you have a sample mean of 25, right? So think about it. You've got a sample of 40 numbers. The sample average is only 21. And based on that fact, how likely for the statements to be true such that the average of all 100 numbers is 75? Okay. So I hope your answer for the question I had is that it's quite unlikely. All right. I hope that you will say, look, if the sample average is only 21, then it's unlikely for the average of the whole population, which is 100 numbers, to be 75, right? So if you got that answer, then you are on the right track. Okay, I would say good job. So let me type it up. It is quite for the mean of the 100 numbers to be 75. And if you kind of intuitively thought about that, but didn't really know why is that the case. So let me explain a little bit more. Okay, why it is quite unlikely for you to have a sample mean of 75 if you, why it's quite unlikely for you to have a population mean of 75 if your sample average is 21. All right, so look, you randomly draw 40 numbers from the population, right? And the average of the 40 numbers is only 21. Now, if you put these 40 numbers back in the population, and for the whole population to have an average of 75, that means the remaining 60 numbers that you didn't draw must all have high numbers, so that when you mix them together, the average is as high as 75, right? You might say, oh yeah, sure, that's possible. It could be that I draw 40 numbers, all of them are small numbers, and the rest of the 60 numbers are big numbers. Yes, I agree, it is possible, but now what we're asking is it likely? If you randomly draw numbers from that box, is it likely that you are so lucky or so unlucky that you got all the small numbers out, 40 of them? You probably say no, right? It's unlikely for you to randomly draw numbers and you draw all the small numbers. Actually, if you are that good, then let me know, because you can definitely help with lottery drawings, right? So that is why we say if the sample average is very small, like 21, then it's unlikely for the population average to be high as 75, right? So let's move to the next one, the next round. What about 45? You draw another 40 numbers, and this time you find the average of the 40 numbers is 45. How likely can that happen if we assume the population average is 75. Okay? Well, I hope this time you're gonna say it is still unlikely, but probably not extremely unlikely. So it is unlikely for the mean of the 100 numbers to be 75. And the reasoning is similar to what we just talked about. Look, if the average for the 40 numbers in a sample is 45, then that implies for the remaining 6 numbers in the box, they must have still high numbers such that when you mix the 40 numbers and the 60 numbers together, their average to be 75, right? But this time, in comparison to the first round, we don't require the 60 numbers left in the box to have extremely high numbers, because look, 45 and 75 are not, the difference between 45 and 75 are not that high, right? But we still require the remaining 60 numbers to have really high numbers so that the average of the whole population is 75. All right. Now, one last round, then we can get to the concept of p-value. We haven't got there yet. So one last round, what if the average you've got from the 40 numbers is 73? Think about that. So 73 actually is close to 75, right? And this time, you might say, oh, okay, if my average from the sample is 75, then it is likely for the average for the whole population to be 75, right? Because when the 40 number average to 73, then you don't require the remaining 6 numbers in the box to have high numbers. Okay, they can just have relatively high, such as 77, 79. You don't require them to be 100 something, right? Then when you average all numbers together, the average can be 75. So in this case, okay, we're gonna say it is likely. It is likely for the mean of the 100 numbers to be 75. All right. Now, as you can see, as the sample mean increases from 21 to 45 to 73, our judgment about that statement changed. At the beginning, we say the judgment is unlikely to be true. Then we say for 45 as the sample mean, we still say it is unlikely to be true, but it's in comparison to 21 is relatively kind of more likely. And finally, when the sample mean is 73, this time we believe it's likely for the statement to be true. Okay, so when we say quite unlikely, likely, quite unlikely, likely, and when we say quite unlikely, unlikely, likely, we are actually describing the p-value. For the quite unlikely scenario, in this case, actually, we're implying that the p-value is small, okay? Because p-value measures how likely can we get this sample mean. Okay, how likely can we observe this sample mean if the null hypothesis or if the statement here is true? If we assume the null is true, how likely can we observe a sample mean of 21? Turns out it's unlikely, and in that case, p-value is small. For this case here, for 45, we still say it's unlikely for the statement to be true, but this time the p-value is not as small as the first case, so p-value is relatively small. I'm going to say relatively small. All right. And then lastly, for this case, when we for 73 as the sample mean, we say it's likely for the mean of the 100 numbers to be 75. In this case, we say p-value is large because there's a high probability for us to observe a sample average of 75 if we assume this statement is true. That is, the mean of the 100 numbers is 75. Of course, I just realized I have a typo here, and I'm sure you can kind of figure that out. But it should be the THE, not he. I guess it's kind of like a typical typo. At least for me, it's typical typo. All right, there we go. All right, so that's the concept of p-value. But how can p-value help us to make the judgment when we test hypothesis? Well, look, the hypothesis I have here, the mean of the 100 numbers is 75, can be regarded as a null hypothesis, H0, okay? And we figured that when we have a small sample mean, we say it's unlikely for the null to be true. And that corresponds to a small p-value, all right? And therefore, when the p-value is small, we can safely reject the null hypothesis. Okay, reject the null hypothesis. Or in other words, when the p-value is small, we can safely say that this null hypothesis, this statement is unlikely to be true, right? If the null hypothesis is unlikely to be true, then we can reject it. That's the idea. Now, for this one, when p-value is large, that corresponds to a situation where we have a relatively large sample mean, and we say it's likely for this null hypothesis to be true, and this is the scenario where we will not reject the null hypothesis. Or, in other words, we fail to reject the null hypothesis. So that's it. That's how far we will go in terms of learning p-value, the concept of it, the idea behind it. Eventually, after this analysis we have here, so this is what we can tell in the future. All right, p-value measures how likely can we observe the sample mean from the sample data if we assume the null is true. If it's unlikely, then we will definitely get a small p-value, and that's the case where we're going to reject the null hypothesis because it's unlikely for us to observe what we did observe in the sample data. There must be something wrong. Either the sample data is wrong or our assumption, which is the null hypothesis, is wrong. Then not. Unless you have some mistake during a calculation, you wouldn't question your sample data. You're going to go back and question the assumption you made. At the beginning, maybe the assumption was wrong, right? So if p-value is small, we're going to reject the null hypothesis. Now, look, on the other hand, if it's likely for us to observe the mean from the sample while assuming that the null hypothesis is true, then we will observe a high p-value, and in that case, we will not reject the null hypothesis. So to summarize that, we're going to say when p-value is large, we will not reject the null hypothesis. And the next page actually kind of summarizes what I just talked about. When p-value is low, we reject the null, and correspondingly, if we can reject the null hypothesis, that means we actually find enough evidence in support of the alternative hypothesis. In our example on the previous page, it may not occur to you that way. Now, don't worry, because for this course, the idea is not for you to fully understand p-value hypothesis totally. It's just an introduction for you to have an idea about this concept and this tool, right? However, whenever we can reject the null hypothesis, we can conclude enough evidence is found in support of the alternative. Now, on the other hand, if p-value is high, that tells us we can't reject the null, and that also tells us, look, we didn't find enough evidence in support of the alternative. Of course, a key question is, when we say p-value high or low, how can we make the judgment? What p-value is high? What percentage is high enough for us to say it's high? Well, here's the criteria. Here comes our alpha, which is the significance level. So if p-value is less than alpha, in that case, we're going to say p-value is low. And in that case, we're going to reject the null hypothesis. So this actually summarized to p-value less than alpha. And on the other hand, when p-value is high, this actually summarized to p-value greater than alpha. That's when we say p-value is high and we don't reject the null hypothesis. And it's extremely important, at least as of right now, for you to remember the criteria here, because you're going to apply this criteria later on when we talk about regression analysis. And this criteria applies whenever you perform hypothesis test, right?